Hello everyone. I would like to present you Ayşe Verda Irmak from Bilkent University. She's a last year bachelor student there. This summer we studied cyclicity problem in the Hardy spaces, a classical result by the Beurling. So yeah, I'll leave the ground to Ayşe and she will continue. Good luck.
As my mentor mentioned, these functions, and here is the outline for my presentation. First, I will give you an introduction. It's kind of preliminary section, and then I will be stating the goal of our research. And then I will introduce Beurling's theorem, and then we will prove the theorem. And then lastly, we will state the criterion for cyclicity definition of H2D. And then I will show you my reference.
Apologies. Can you use the microphone because we cannot hear you over the Zoom? Sorry for disrupting.
Microphone is open, I think. Can you hear me?
Yes, now it's perfect. I can hear you very well, but when she speaks, we cannot hear.
Maybe Ayşe can speak louder.
Sorry.
It's fine. So many of you probably are familiar with these concepts, but I didn't want anyone to get lost in the presentation, so I included them anyways. First is a bonus space. A bonus space is a complete normed vector space, meaning that it's a vector space equivalent to the norm, where every Cauchy sequence converges within the space. And a Hilbert space is a bonus space with an inner product, which allows us to for a concept for angle and orthogonality and so on. And a linear operator is a mapping between vector spaces that preserves operations of vector addition and scaling. And next is a Hardy spaces. Hardy spaces are a type of Hilbert spaces, denoted HPD. They consist of holomorphic functions on the unit disk B, with the given condition, the norm being bounded. And the space that we worked on, which is H2D, consists of functions with square integrable boundary values. And the inner product of two functions in H2D is defined as follows. And what are cyclic functions? They're defined as let B be a bonus space and T a linear operator, bounded linear operator from B to B, and F a vector in Z. Then we call F cyclic with respect to the operator if and only if the closed span T to the n F, where n is a positive integer, is equal to the space D. And we study cyclic functions in H2D with respect to the shift operator, and shift operator is defined like this. Where for input fz, we get the output that times. It's a very basic operator to understand that first glance. Now, Schwarz integral formula for a function f, holomorphic on the closed unit disk. The Schwarz integral formula is like this, and it helps us to reconstruct the holomorphic function inside the disk up to an imaginary constant, only by knowing the real part of its boundary, values. And Blaschke products. Blaschke products are infinite products used to construct bounded analytic functions with prescribed zeros in the unit disk. And an important subject, inner and outer functions. Inner functions are analytic functions on the unit disk with modulus 1 almost everywhere on the boundary. And outer functions are non-vanishing functions in the unit disk. And they are determined by their boundary values. If you look closely, the first part of inner functions resemble Blaschke products because it's a Blaschke product. It helps us separate the zeros of the function. And inner outer factorization. Let fz be a function in the Hardy space, HPD. Then fz can be uniquely factored into iz times oz, where I is an inner function and O is an outer function, and this is really important. And now, what's our goal? The goal of our research was to answer the question under which conditions we say a function f and h2e is cyclic compared to the shift operator. So to give you a more explicit image, for which functions f and h2e, any function g in h2e can be approximated by a polynomial multiple of f, which can be written like c0fz plus c1zfz plus c2z2fz and so on. Before going into more detail, I will introduce a more intuitive approach, which is the Wiener criterion, and it states that function h2e must not have any zeros inside the unit disk. So think of it like this. Suppose f has a 0 at point A, then any polynomial multiple of f would again have a 0 at that point. So we wouldn't be able to approximate any function g without a 0 at that point. So even this is a necessary condition, it's not enough for us. Even without zeros, a function may fail to be cyclic. So this is where we introduce Beurling's theorem. The theorem states, let fg in h2e, and g belongs to f bar, which is the closed linear span of z to the nth set, if and only if the inner factor of f is a divisor of the inner factor of g. In this case, divisor means that if like f0 divides g0, then the quotient is in h2e and it's an inner. Now we can continue with the proof of Beurling's theorem. We will start with the reverse direction. Assuming that the inner factor of f divides the inner factor of g, we need to get g in CF bar. G in CF bar means that the norm f minus g less than epsilon p is. And with the factorization f equals f0 times f1, where f0 and g0 are the inner parts and f1 and g1 are the outer parts. We can rewrite this norm as cf1 minus h0 g1, h0 is g0 divided by f0, basically we divide the return by f0. And we can substitute this into the inequality above, and we get the norm pf1 minus h0 g1 is less than epsilon. And now we reduced our problem to showing CF1 bar is equal to H2E, because like if you look at the inequality, a polynomial multiple of F1 is close enough to any function X0. And in order to do this, we will introduce a system of equations, the inner product of Z to the n F1 and K equal to 0 for all and greater than or equal to 0. If this has no non-trivial solution in H2E, other than K equals to 0, we will reach our goal showing CF1 bar is equal to H2. To analyze this, we will use Fourier series expansion. We will define the coefficients Cn as C. And the series when constructed with these coefficients is actually equivalent to the Fourier series expansion of F1K bar. And we construct an analytic function psi in the unit disk, within the unit disk coefficients, and psi has. And by, again, the inner and outer factorization theorem, we have psi equal to psi 0 times psi 1. Psi 0 is the inner and psi 1 is the outer part. And by the properties of outer functions, the outer part of a function is always greater than the function itself. So we can write this inequality where psi is less than or equal to psi 1, which is equal to f1 times k1. And we can send f1 to the other side to get a bound for psi over f. Since f1 is an outer function and both psi and f are in H2E, the quotient psi over f1 is also in H2E and it's bounded by k1 and so on. And by the first property of psi, and by taking the conjugate value of the right-hand side of it, we see that all the Fourier coefficients of k vanish, plus k is equivalent to 0, and we have concluded our proof, reverse direction of the proof, CF1 bar equal to H2B. Now we have to handle the forward direction. We need to show that if G is in CF bar, then the inner factor of G must be divisible by the inner factor of F. We will do this by assuming to the contrary that G is in CF bar and G0 is not divisible by F. We will introduce a new variable MR, which denotes the minimum of the modulus of the inner factor of F0 on the circle with radius R for some R inside the unit list. We choose this R such that this number M is strictly positive, which means F0 on the circle always yes. And under the assumption that G is in CF bar, we can again write this inequality where the normal is less than epsilon times M since M is less. And we will let H equal to G0 over F0. This quotient is important for us because if G0 is not divisible by F0, then H wouldn't be in H2D and it wouldn't be an inner function. And our aim is to derive a contradiction. And then on the unit circle, on the circle with radius R, we can rewrite this inequality like this: the norm of F1 minus Hg1 less than epsilon. We divided the left-hand side with F0 and the right-hand side with M. And by Minkowski's inequality, we get the norm of Hg1 less than the norm of F1 plus epsilon. And now we bounded Hg1. And from this, it's obvious that the function Hg1 is in H2D. And since H is 1 by definition almost everywhere on the boundary, G1 must be the outer factor of Hg1 and H, the inner factor now, which is the contradiction that we were looking for. H0 is divisible by F0. And this is the end of the proof. So what about cyclicity? Up until now, we all talked about like which functions G in H2D belong to CF. But we need to determine the condition for which functions F, CF bar is equal to H2D. And in light of Beurling's theorem, we know that the inner factor of F plays a crucial role in determining whether a function G in H2D belongs to CF bar. And to determine when F is cyclic in H2D, in other words, when CF bar is equal to H2D, we need for every function G in H2D to belong to CF bar. And this is only possible if the inner factor of F, which is F0, divides any possible inner factor G0 for all G. And which means F0 must be the trivial inner factor, which is 1 in this case, meaning that F has no inner factor. So in more formal terms, we can say that a function F in H2D is cyclic with respect to the shift operator, if and only if. And this was the result that we wanted to get for our research. And this is the end of the presentation. And here are my references.